Hi, I'm Rajiv Tipnis, and this is a presentation for my final project at Harvard Extension School's Big Data Analytics class, and my topic is mobile analytics. So, what is mobile analytics, and why is it a big data problem? Top US carriers like AT&T and Verizon each have more than 100 million subscribers. Agreed, they're not all smartphone users, but the total US smartphone subscribers are close to 150 million now, almost half the population. And carriers are each generating more than 10 billion records or a trillion bytes per day. And this data growth is going to go on in the next several years, amazing, amazing pace. So, what kind of questions can one ask out of this data? So, and what questions are important to ask? Different people want to ask different questions, but I've sort of listed down some here, like what is the growth rate of smartphone users? What is the distribution of usage of smartphones? iPhone 5 versus 4 versus Samsung. A new device gets introduced. How is it performing? Which sites and apps and brands are popular? How much data is being consumed by subscribers? Broken down by devices, by apps. And what is the behavior of mobile user? What apps do they like? And can we predict which apps they will buy based on what others like them buy or use? So this has traditionally been done using data warehousing architectures, and the data warehouse architectures have been traditionally done using three types of technologies. One is essentially like a star schema where you take a fact table and dimension tables, and you do aggregations of data around the fact table and put that in a relational data model. Um, and the same model can be then put on a really massively parallel processing system like Teradata or Netezza. And they are expensive systems, but this kind of technology does provide answers to the questions around big data. Um, but with the advent of Hadoop and related technologies, the same ability can be made to be put on sort of a commodity hardware, right? So Hadoop is a distributed parallel processing. It's got built-in redundancy, fault tolerance. It's also MPP, but it can run on commodity hardware. Now the other difference here is that not all Hadoop technologies solve the same thing. So Hadoop and HDFS, it's a high latency batch processing oriented. So it allows for ad hoc queries, but it's not really good for interactive queries. While once you put a database on top of a file system, then you can do fast read and writes. Especially if you're using the NoSQL Cassandra like databases and do interactive queries. But the downside of these databases is that they're not really optimized for ad hoc queries. So in this project, what I want to do is use two technologies, Pig and Cassandra, and to use these technologies to run reports. And in this particular presentation, I'm going to focus on one report. So what I did was I took the mobile usage logs and stored the logs into the Cassandra file system, and I queried them using Pig, just as we did in one of our classes. And then Cassandra was the big learning experience for this project because we didn't really learn it during our classes. And I spent most of my time learning about Cassandra. And so I created an equivalent Cassandra database key space, loaded the logs into Cassandra using some Python packages like PyCasa and CQL, which I'll talk about. And I queried the Cassandra with CQL 3.0. And I actually ended up using DataStax Enterprise Server. Initially, I was thinking I'll use my VM or AWS, but I realized that this server is actually available for free for use in development environments, and the installation was very painless. Like it was within 10 minutes I was able to install it. So and for anyone who wants to use my presentation to then recreate it, it's going to be a breeze if you were to install this particular server, and it's free, so you should be able to without having to pay for development use, obviously. So this slide is a little busy slide, but I wanted to show how the traditional data flow is different from your big data flow and what I've done in this project in relation to the traditional data flow. So in traditional data flow, you would take raw mobile logs and then transform them and create the map logs and then put them into a star schema into an RDBMS-like database. In big data flow, you would take the same logs, and I haven't done this. I've taken the mapped logs for this project, and I put them on the CFS, which is the Cassandra file system, and I also put them on a Cassandra key space. And I ran reports on them using CQL on the Cassandra and using PIG on the CFS, and I was able to compare the reports and saw the results to be the same. And I built a framework where more reports can be added and more combinations of dimensions can be included, which I'll talk about as we go along. Um, so um, I do want to sort of point out here that Cassandra is sitting on top of CFS. So Cassandra file system is actually more reliable than HDFS because there is no concept of a master node. Everything is a peer. All right, moving along. So logs and reports. So the logs the raw logs contain things like URL, hostname, user agent, IP address, timestamp, and the mapped logs are essentially derived from these things. So we were able to derive device model names and vendor names from user agents, for example. So this mapped log field is is the input into my demo system. And for this project, we will use or assume that each row represents a page view. Now, and in this particular presentation, I'm going to focus on one report, which is the top brands by page views. But the code and framework is built to support more reports. Okay. So Cassandra is a distributed, elastic, and fault-tolerant key value store. It's got a ring of nodes. There's no concept of a master or a slave. All nodes are peers. The data model is a store of key and their values. And the first level of values are another set of values, another set of key values like column names and key values. So it provides fast writes, eventual data consistency, which means the data eventually gets written to the disk. And these partitioners are important. Partitioners essentially make the data distribute across the nodes in a cluster in the fashion that you want it to be distributed. So random partitioner, as the name suggests, distributes it randomly, and it's sort of the best partitioner that provides the best use of all the nodes. And Murmur 3 is like random, but it doesn't do encryption, and so it's actually more efficient than random. It's going to be introduced in 1.2 Cassandra version. One way to think about the Cassandra data model is in terms of if you want to think in terms of relational databases. So the key space in Cassandra is related to your database in the database world. A column family is like a table, row key is like a primary key, and column key is like a name, and column value is like a value. But really, you should think in terms of maps. This is a good way to start, but Cassandra is really a map of key values and a map of maps, essentially is how it is. Now, designing these column families, row keys, and values is an entirely different approach from a relational model. It's you have to think in terms of what you want to query. So ad hoc queries are not really a good idea in Cassandra, but once you know what you want to query, then you can really build an efficient column family that can give you the right results. There's no foreign key or joins. Each row can have different cardinality of columns, and application can create columns on the fly. So that's really a cool thing. And single row is never split across the nodes, so don't make your columns like too wide that it spans across the nodes. And there's a concept of a super column, which is on top of the columns, but it's really not as efficient as what are called composite keys, which is what I've used and I'll talk about. So Cassandra data modeling that I did for this particular project has, in this one, that what I'm showing is that the row key that I've selected is the time key, and the brands are my column keys, brand names, and the values are the page views. So it is an efficient way to represent this data. And the time key is essentially using the random partitioner. I'll be able to distribute it randomly across the nodes. Although in this case, I ran it on my Mac, which is a single node, but I hope and plan to do a real test on a real cluster with this. And the data consumed is another metric that one can do using a similar data model. All right, so for next level of reports where you want to see, okay, how many page views were there for Facebook with, for the users who went to Facebook on an iPhone 4S. So now it's a combination of two things. So this combination is also represented using a composite column key, and this is an efficient way of doing it. And it's a very clever way to sort of do aggregations on a specific row. And it was quite interesting to be able to sort of do this aggregation in an intuitive way. Um, so I'll talk more about my tools and code that I used. So I used Cassandra CLI. I used CQL-SH version 3 and used a lot of Python to actually interface with the Cassandra using the PyCasa package as well as the CQL package. So here I'm showing some snapshots of the code. The first snapshot here is really not CQL. This is using a standard Cassandra CLI to be able to create a column family. But this new syntax, which is the CQL3 syntax, is actually more intuitive to people who are coming from the relational world. It is similar to SQL, but not exactly the same. But in this case, essentially, for example, I'm showing that there are three composite keys. So this makes my row key, and these make my composite column keys. And this code is showing an upsert into this table. And I was able to efficiently upsert into this particular table. So one thing that I really ran into, which was the order by. Now, order by was something that has been introduced in Cassandra recently, but it didn't quite work. And there are some people who are talking about it on the net. So they said that the second column in your primary key is what you should be able to order by, and other columns you actually cannot yet. But even that one didn't work for me. So this is something I need to look into. But what I did was I ran the select star, but then used Python to order it in the descending order. All right. So, and this is the pig Latin sample code for the same sort of logs. I essentially take the logs and put them into a variable in pig Latin, and then as we've learned in the class, use the group and for each and order to create the pig Latin report out of it. All right, I'm running a little late, so let me hurry up here. So this is how you would sort of use my code. CD to Cassandra, run the Python scripts to load and query, and run the DSC, which is the Data Stack Exchange Server, and run the Hadoop on it. And my outputs, they matched. So this particular report, exactly the same on both using Cassandra and Pig Latin. All right, so in conclusion, this project has allowed me to explore and investigate big data technologies such as Pig and Cassandra. And beyond this class, I plan to run this on a real multi-node cluster. I want to revisit some of my decisions regarding the primary and composite keys. I want to play with them in a real cluster. I plan to continue to add more reports on top of this framework, and I also plan to implement some machine learning algorithms. But I had a great time learning and playing with this, and I hope you enjoyed my presentation as well. If you want to know more about it, please don't hesitate to talk to me about it, and thank you very much.